Hi, my name is Emily Riederer, and today I'm here to talk about observational causal inference and why I believe that it's a powerful complement to experimentation in every industry data scientist's toolkit. Regardless of where you work, from pharma companies testing new drugs to e-commerce companies testing new growth initiatives, countless analytical roles require us to tackle problems of measurement. We want to know if whatever strategies we're implementing in the real world actually obtain a desired result. Historically, the gold standard for measurement and evaluation has been the randomized controlled experiment, or as we tend to call it, A/B testing. The essential framework that I'm sure all of us are familiar with is that we take an undifferentiated population and apply the spark of randomization to assign otherwise similar individuals to treatment and control groups. Then we can take the treatment group and apply some sort of new strategy or program, like a drug or a marketing campaign, but withhold it from the control group. Thanks to randomization, we can then credibly understand the outcome of our treatment simply by comparing the outcomes of these two groups. However, despite the ubiquity of A/B testing, it's not always practical or an optimal way to measure causal effects, especially in industries like consumer finance. Testing may not always be feasible if disparate treatments could create a bad customer experience or create ethical or regulatory risk. Testing may also just be hard to pull off. For example, in digital experimentation, it can be surprisingly challenging to uniquely and consistently identify a person across browsers or devices, or to isolate a treatment effect to only some members of an interconnected social network. Testing can also be prohibitively expensive. We might wish to know the impact of a risky or highly capital-intensive strategy, but hesitate to treat enough individuals to take that read. Alternatively, if we're so confident our tests will show an effect, we might not want to bear that opportunity cost of withholding it from the control group. And that's not even to mention the reality of the technical overhead of configuring and deploying experiments, which creates implementation cost. Finally, and perhaps one of the most damning causes of all, is that testing just isn't efficient. Often in finance, we care about value accrued over long-term investments and relationships, but we don't want to drop an A/B test and have to wait months or years for the results. There's no making up for the experiment that we didn't run 5 years ago. That's exactly why I find methods of observational causal inference so compelling. This rich set of methods allows us to credibly measure causal effects from existing observational data without the need to go collect new data through direct experimentation. We do this by replacing that spark of randomization with other sources of semi-random variation between people who did and did not receive the treatment in the past deployment of some strategy. We can then strive to recreate that magic of randomization by supplementing this semi-random variation with reams of historical data, statistical techniques, and domain-driven assumptions. Ultimately, this allows us to construct a counterfactual pseudo-control group that we can compare to the treatment group in the same way we would have as if we'd run that experiment. While these techniques largely originated in fields outside of industry, like public health and political science, I actually believe that industry has many distinct advantages when employing causal techniques to recreate that spark of randomization. And that happens for a couple of different reasons. First, in industry, we have a lot of these sources of semi-random variation that we can exploit, because our business strategies often have clean and somewhat arbitrary cutoffs based on our customer segmentations, timing of new product launches, or other operational constraints. These arbitrary sources of variation are also generally well-known and well-documented in our CRMs. In fact, even past execution mistakes can be a powerful source of variation, which I like to more charitably call natural experiments. Second, industry datasets tend to be richer and more consistent. Social scientists often have to work with secondhand data like censuses and surveys, which may be lower resolution with fewer features and time points on given individuals. Ideally, in industry, we have integrated data warehouses that give us a consistent view of our population of interest, typically our customer base, across time and across a wide variety of data concepts, like digital data, spend history, telemetry on responses and adherence to past campaigns, etc. This data helps us carve out these pseudo-experiments and gain more confidence in our results. For example, we can rerun our analysis on out-of-time data and conduct a placebo test to ensure our methodology recovers a null result when we wouldn't have expected to find a causal effect. And finally, beyond that quantitative data, we also have more qualitative information. Our clear-eyed view of precisely how our past strategies went to market and were designed and implemented allows us to reason about whether critical yet statistically untestable assumptions hold. If any of this sounds intriguing to you, what I'm here to talk about today is common causal inference design patterns. While this is by no means a comprehensive survey of this fast-growing causal literature, understanding a few of these basic techniques and approaches and designs can help industry data scientists recognize when they have a problem that they're facing that could be solved by causal inference. I don't claim to teach these methods in complete depth in the next half hour, but my hope is that this bird's-eye view can aid in pattern recognition and motivate someone to dig more into the details when they encounter a problem that feels relevant. After introducing a few of these basic patterns, we will see how they can also be regarded as building blocks for a much broader and richer modern causal toolkit. And we'll discuss how data practitioners like you all can set up your orgs for success with causal inference. But first, let's hit on the basics of a few of these key design patterns. 4 of the patterns that we'll discuss today are stratification and propensity score weighting, which are both versions of extracting a randomized experiment hidden in a broader trove of observational data by fixing imbalances in the distribution of who did and did not receive that treatment. After that, we'll look at regression discontinuity and difference in differences. These allow us to extract causal reads from increasingly disparate populations. But first, let's start at the very beginning with basic stratification. This can be a useful pattern when you have similar treated and untreated individuals, but you know that the groups differ on a couple of key dimensions. It generally works by trying to bin data into more comparable subpopulations. Basically, the recipe is to bin our population into subgroups based on factors that might simultaneously influence both who received the treatment and how they performed on our outcome metric of interest. In theory, then, within each of these subgroups, the treatment and control observations should be more comparable. We can then calculate that causal effect that we care about, the difference between the treatment and the control, within each subgroup. And finally, then, we can reweight those strata-level causal effects to that overall population distribution. This works so long as we can stratify on all those dimensions that capture the important common causes of our treatment assignment and the outcome, and so long as all strata have both some treated and untreated observations within them. So as an example here, imagine that we run an e-commerce platform and try to A/B test a one-click instant checkout experience on Black Friday. But as I mentioned before, sometimes A/B testing is hard. Due to some sort of glitch in our code, the treatment assignment might be correlated with what browser our customers were using. Chrome users perhaps see that button more often than Mozilla users. And because browser choice can be correlated with other demographics and characteristics, perhaps we know that on our platform, Mozilla users spend less money on average. So we have this choice of browser that confounds both the treatment assignment and our outcome of interest, and we no longer have a valid experiment. Addressing a problem like this with stratification, we could recover the causal effect of showing users that one checkout button by conducting separate analyses for the treatment effect within the Chrome user group and the Mozilla user group, and then weight averaging those two subgroups together to understand and recreate that overall effect. Of course, stratification is only going to work best in those simplest of cases where we can make those relatively comparable subgroups by bending on just a few different strata dimensions and variables. Often, due to either direct strategy implementation or consumer self-selection, our treated and untreated groups may be unbalanced across many more continuous or linked dimensions that we can't just bin away into that nice little grid. In a situation like this, we can graduate from stratification to the related but more mature method of propensity score weighting. This method attempts to rebalance treated and untreated individuals across many latent variables to make them more comparable. So when simple stratification cannot help us formulate sufficiently comparable groups, we can instead follow this propensity score weighting recipe. First, we can model the probability of each individual being in the treated group based on many underlying characteristics about them that we suspect are a common cause of the treatment and the outcome. Then we can take our model predictions and derive individual level weights that allow us, essentially tell us how similar each untreated individual is to the overall distribution of individuals within the treatment population. Finally, we can apply these weights when calculating those average outcomes for the treated and untreated populations, and then compare the two average outcomes as before. And this method actually has very similar assumptions to stratification. To bring propensity score weighting to life, let's consider a scenario where this method could actually come in and save the day. So suppose we send a text message to all customers for whom we have a valid phone number on record, and we want to measure if this influences their likelihood of a next purchase within some time period. Here, we didn't even try to run an experiment, and we probably don't want to compare the treated and untreated groups superficially, because the type of customer who wouldn't even bother to give us their phone number probably tends to be less engaged already and has less likelihood to make future purchases. So the treatment of receiving that text message and the outcome of engaging with our brand is confounded by this underlying signal of loyalty and engagement. Following the propensity score recipe, we could build that model predicting the likelihood of someone having given us their phone number based on demographics, past purchase behavior, past engagement data about how they've related to our brand in the past. Using our model, we would then derive weights that reflect how much each member of that no-phone population looks and behaves like the type of customer for whom we do have their phone number. These weights help balance our populations and would make them more comparable. So then finally, we'd return to the calculating a credible estimate of the average treatment effect by comparing that average outcome in the treated and this reweighted, sort of resampled control group. While stratification and propensity score weighting are very powerful tools, they do rely on that really critical assumption that we have generally similar individuals in both our treated and control groups. They're just somehow imbalanced. Of course, sometimes we aren't as lucky as to find that hidden experiment within our data. The populations of treated and untreated may be truly disjoint. In fact, in industry, we've often caused that sort of disconnect. Many companies offer customers differentiated treatments based on discrete customer segmentations, based on model scores or sharp cutoffs on behavioral metrics. This can create a situation where our entire treated and untreated populations are completely disjoint, but we can actually exploit that arbitrary cut point and the arbitrary break between the two customer segments itself to measure local effect with regression discontinuity. This approach makes the bet that while the full spectrum of the treated and untreated individuals may be systemically different, observations right above and right below that cut point may be able to be reasonably compared with just some modest adjustments. So the basic regression discontinuity formula is to first model that outcome with respect to the assignment variable on each side of the cut point. Next, we can evaluate those two models at the cut point value and use the differences in predictions between the two model outcomes as the local treatment effect. To make this work, the assignment rule must be unknown to the treatment subjects, so they're not able to game it and decide which side of that line they ended up on. And we must be able to fit a reasonably simple model of the outcome versus the running variable. This is a place where regression discontinuity can often get in trouble because if our models have too many degrees of freedom, They may have odd tail behaviors, which is exactly where we care the most about their accuracy. So, as I said, sharp cutoffs that we can exploit in this way come up a lot in industry, as continuous aspects of customer behavior are binned into these discrete groups for different targeting. So, just one example. Suppose we send a coupon to all customers who made no purchases in the last 90 days, and we want to assess if that increases their spend throughout the next year. We might not believe that a customer who's last spent 2 days ago and one who last spent 200 days ago can be compared. But if we zoom in at that cutoff point, we can begin to believe that customers who last shopped 80 days ago versus 100 days ago are more similar, and our modeling can help absorb that residual bias from smaller systemic differences. So, applying the regression discontinuity recipe, we'd model future purchases as a function of the time since last purchase within both the treated and untreated populations. We could then evaluate both of those models right at our 90-day cutoff point and compare predictions to estimate the treatment effect. It's worth noting that this method can't tell us the treatment effect for sending a coupon to the entire population, but it can help estimate the local effect for customers who exist right around that cutoff point. And often that's good enough. It would still be a helpful decision tool to decide whether or not we want to continue running this exact campaign, targeting this exact type of population. However, the further we get from our randomized experiment construction, the more we have to worry about where our setup can break down. The challenge of observational inference is that we begin to rely more and more on specific and tenuous conceptual assumptions that can't be tested statistically. For example, if our strategy instead had been having on our website free shipping and returns over $50, customers who expected to need to make returns might self-select into the treatment population by buying an extra item and bumping their overall basket size to $51 from $49. So this would violate our assumption that our strategy is not known or gameable. Notably, this isn't the kind of assumption that is easy to test with rote statistical diagnostics, although there are some techniques such as looking at bunching of values right around that cutoff point. Instead, though, this illustrates the importance of domain-specific knowledge and business context when tackling causal problems. So, regression discontinuity can help when we have those disjoint groups from a single population. But sometimes we have access to even less detailed information. We may have completely disjoint groups that have different behavior, even if neither of them had received the treatment. In a situation like this, we can exploit the difference in treatment timing to still get a read on causal effects with the final pattern that we're going to talk about today. This is exactly what difference in differences tries to accomplish. And the main idea here is that we can compare the difference not just between treated and untreated groups, but also across time periods within each group. The name difference in differences largely gives away the game here, but I'll walk through the recipe to be slightly more precise. For each of the two populations, we look at the difference over clock or calendar time and how the two populations performed before or after one of them received the treatment. The difference between populations of their individual differences across time serves as our estimate, but this is technically done as a fixed effects regression. The critical assumption here is that the one group had not received treatment. The two groups would have had parallel trends. And there are a few different ways this assumption can break down, depending on how it was determined who got the treatment and how well isolated that treatment actually is. And we'll come back to those in a minute. But first, let's consider one example. Suppose we want to know if remodeling a store materially changes traffic or customer visits to that store. Of course, like we said at the beginning, sometimes experimentation is just too expensive. It would be wasteful and impractical to make a large capital investment in remodeling many branches of our store at random just to know that causal effect. Instead, we could take a remodeled store and a non-remodeled store and compare their performance over time. The difference in their performance trend before and after the one store was remodeled then can become our point estimate of that causal effect. But once again, these increasingly low-resolution methods are predicated on the accuracy of untestable assumptions. Two key ways we can violate difference in differences parallel trends assumption are the decision to treat and spillover. If the decision to treat a store was directly motivated by anticipated increase in store visits, for example, knowing that a new bus station was going in right in front of the store, then we violated the parallel trends assumption. We would expect that the treatment store would have seen higher traffic and a different trajectory even if it hadn't been treated, so the comparison's no longer valid. The other common way we violate parallel trends is due to spillover. If the trend of the untreated store can be affected by the treatment. So for example here, if we were comparing two stores in the same neighborhood, that effect might not be well isolated. Customers from the non-remodeled store might defect and go to the remodeled one instead, so that same decision point and behavior would be inversely driving the trends of both stores at the same time. And this would invalidate the assumption and overestimate our overall effect. Some modern modifications of diff and diff help relax these concerns, and we'll mention those briefly in just a moment. But first, to conclude this section, let's reflect on our tour of these 4 basic design patterns. Hopefully these patterns and recipes help illustrate the different types of variation, data, and context we can bring to bear in causal problems to help recreate that magical spark of randomization. Of course, this is only how the story begins and certainly not where it ends. These basic causal patterns serve as building blocks for many exciting modern methods that help us answer increasingly interesting questions or relax restrictive assumptions. I'll take the next few minutes each to just talk about a few of the ways these approaches can scale up. First, propensity scores can be used to measure a much wider variety of causal effects beyond just the average treatment effect. With the same propensity model, we can calculate weights in different ways to estimate the effect on different populations. We can simply measure the average treatment effect on the population that we did treat to simply measure whether our past strategy was or wasn't successful. Or we can extrapolate that average treatment effect to the population that went untreated or to the entire population. These other weightings can help us answer more prescriptive go-forward questions, like whether we should expand a strategy or focus on finding ways to reach out to individuals who, for whatever reason, weren't initially impacted by our treatment. Similarly, we can use propensity scores to explore results in only a subgroup of a treatment population. Often, we'll run into situations where we randomize at one step of an experiment. For example, an airline offering customers the opportunity to enroll in some sort of challenge to earn so many miles over a fixed time period. But the effect we care about is not the effect of the offer, but the effect within the population of those who enrolled. However, since enrollment is a self-selected subgroup of the treatment population, we can't believe our fully randomized control group is the most apt comparison to that self-selected subset of the treatment group. So propensity scores could help us find that right subpopulation within our control to continue measuring a different experiment in a different estimand within that broader experiment. Of course, it can also be myopic to think solely about the average treatment effect. To improve segmentation, targeting, and personalization, we often want to understand the distribution of the effects and estimate treatments at the individual level. Propensity scores play a prominent role in many popular methods for estimating heterogeneous treatment effects, such as causal forests and doubly robust estimators. In the case of causal forests, propensity scores combine with the power of machine learning techniques like random forests to recreate many experiments within every leaf node of the random forest trees. Another approach is doubly robust methods. Such methods provide a framework for combining individual level predictive models of the treatment likelihood and the outcomes under different treatments. And they come with this neat, miraculous property that they're robust to misspecification of either the propensity or the outcome model. That is, to a certain small extent, we're actually allowed to be a little bit wrong and still recover a credible result. Regression discontinuity and diff and diff also have many fascinating variants that help make these powerful yet somewhat unforgiving methods more flexible to different and more realistic contexts. Fuzzy regression discontinuity extends the regression discontinuity framework to situations where there isn't just one sharp cutoff, but rather a more gradual switching between untreated and treated individuals across that running variable. On the diff and diff side, the literature here is so active and fast-changing, it's hard to pick just one example to hit on. But one popular approach that I'll highlight is Bayesian structural time series modeling, which extends the general framework of comparing groups, both between groups and across time, to problems with more complex trajectories than parallel trends, incorporating trends, seasonality, and so much more. So if any of this sounds interesting to you, or if you're beginning to wonder how your organization can better use causal methods, I think it's worth exploring what proactive steps we can take to set up our organizations for success. Hopefully, the preceding discussion illustrates that causal inference is more than just a statistical tool. To be successful, it definitely requires a lot of rigorous statistical and probabilistic thinking, but beyond that, it's also very imperative to have high-quality data to detect and remediate different sources of imbalance and bias that we've discussed, and a lot of domain context to really interrogate whether we believe our assumptions hold. And those begin to sound like issues of data quality and comprehensive information management. So ultimately, the key to success in causal inference has strong ties to having a good culture for data, metadata, and knowledge management. And we can map some of these ideas back to some of those core patterns that we've already discussed. In propensity score weighting, we saw the need to access high-quality features which characterize the common causes of an individual's likelihood to receive treatment and their outcome. Creating such features is greatly aided if we have strong data management and a centralized source of truth, which gives us a 360 view of our customers, including entity resolution and universal join keys that allow us to bring together multiple aspects of customer behavior, like digital, operational, and performance. Regression discontinuity methods similarly illustrate the need for metadata management. Operational data about how past campaigns and strategies were run and segmented, being preserved in a machine-readable format, can be an invaluable way to find those sharp cut points that we can exploit and help future data scientists answer questions that today we can't even imagine they'd want to know. And finally, diff and diff, which shows the importance of qualitative information, like that decision we talked about of which stores should get remodeled. These can be critical in detecting potential assumptions violations, and so really illustrate how knowledge management in the form of democratized access to documentation about key business decisions can be another invaluable resource. Speaking of resources, as we wrap up our time together today, I'll end with just a few words on where to learn more. The final slide in my deck contains my personal contact information, links to my blog, and more importantly, many excellent open access resources that I found useful in building and sharing a causal toolkit. These include excellent free textbooks coming from economics, public health, and machine learning perspectives that are an excellent way to get a cross-disciplinary perspective on the foundational and state-of-the-art techniques that are available. So, in closing, I really hope this presentation causes you to add a few new causal tricks to your toolkit. But then again, I guess I'll have to track down some data on conference participants who didn't attend this session to find out for sure. Thank you for your time.